This is lecture number 16 of the course Engineering Mechanics. In the last class, I showed that if we have a line distributed force system acting on a rigid body, say AB, then we can get the wrench of this force system by putting a force Fr, single force Fr, at location XR without the presence of any further torques on this force system too. Now this line distributed force system is characterized by this function Flx, where Flx is this curve shown here. I showed that this Fr turns out to be the area under the FL curve, area under the Flx curve. Sometimes I call this curve as the loading curve. So the RB has been loaded by a line distributed force characterized by this curve. So I call this also as loading curve. So Fr turns out to be area under the Flx curve, and XR turns out to be the x coordinate of the centroid of the area under the loading curve. This interpretation of Fr in terms of area under the loading curve and that of XR as the x coordinate of the centroid under the loading curve could prove to be very handy while trying to find the equivalent force systems of some line distributed forces. What are those line distributed forces? Suppose I have a line distributed force which is having its FL curve as the side of a triangle like this. So you go to any location X, the value of FL at that point is a constant, and that constant is this. The magnitude of this force vector or magnitude of this force, line distributed force at the left end, and the unit of A is of course Newton per meter. And here I am taking the length of the RB as B, right? Now if I have to find the equivalent force system for this line distributed force, it's going to be one single force acting at XR. Since I know Fr is the area under the loading curve, and the loading curve is very simple here, the loading curve is such that the area under the loading curve is a triangle, right angle triangle, I can find Fr easily as half AB. It will be in newtons. How is it helping me? It is helping me, this realization is helping me in a way that I do not have to perform the integration right now. The area under the loading curve is simple. We are aware that the area of a triangle like this would be half AB. I write FR directly. Then XR I know is the X coordinate of the area under the loading curve. Now the centroid of this triangle will be somewhere here, C star, and it will have its X coordinate at B by 3. This is again this is a result that we are aware of already. This I marked as X. So I am saying that this, the X coordinate of the centroid of a triangle, we know that it is at B by 3, and thus I can directly say that this force should be applied at B by 3 meters from the left hand side. If we consider one more example in which the loading curve is uniform, right, and let this be A Newton per meter, the length of the body is B. I can replace that by one single force Fr at XR. Fr is the area under the loading curve. Simply AB newtons. And what would be XR? XR would be the X coordinate of the area under the loading curve. And we know that since the area is simply a rectangle, its centroid should be here, and the X coordinate of that will be B by 2. So you need to put XR, that single force, at B by 2. Okay. Now I want to go back to a slide that I showed in the previous lecture. This slide, I was saying that there are some special force systems for which CRW turns out to be 0, and the wrench is comprised of one single force acting at a special location. I said that there are some force systems for which this is possible. I gave one example of a coplanar force system, and then later I gave an example of a distributed coplanar force system as well. Now I want to pay some attention to the parallel force system, and I want to take an example of a volume distributed force system, which is also a parallel force system, and I want to show that the wrench has no torque component. I covered, so we'll say wrench of a volume distributed force system, and the example I am going to take is of gravitational force. Gravitational force. So let's consider an RB close to the surface of the earth such that at every point on the RB there is a small force dF acting, which is density of the material at that point multiplied by the small volume that I have taken at this point, and then there is this gravitational force acting downwards. So G is downwards. Such a force system is called a parallel force system. So this is not only an example of a volume distributed force system, this is also an example of a parallel force system. At every location, the force vector is parallel to the same vector E, and that vector is pointing downwards. Okay. I want to replace this force system by one single force Fr acting at a special point W, and I am anticipating that CRW is indeed 0. What is this Fr and what is this location W? We want to find what is Fr and what is W. So I impose the first condition of equivalent force system. This is my system 1, this is my system 2. I get let me put this as a vector for the time being, because it's actually the vector that I am seeking. So what is the net force in the first force system? That net force is dF, which is a scalar, E integrated over the whole RB, and on right hand side I have the vector Fr. Now I replace dF in terms of the local density, local volume, acceleration due to gravity, and the vector E. What I get as Fr. Now since vector E is a constant during the integration process, I can pull that out and I have rho G dV equals Fr. Indeed, G is also a constant. And thus I will pull that also out. I get rho dV equals Fr. Rho times dV is simply the total mass of the RB. Total mass of RB. So I get Fr as mg times mg along the direction E. That's the net force. The next question is, where should I put this force? I need to find W. Okay. I want to know mg times C is the net force. I want to know W. How do I find W? To find W, let's take an origin or a point, a reference point, O. Let's go to this point. This is my point. This point P. Right, and at this point I have this force dF acting downwards, which is rho times g times dV. Now the second condition of equivalence requires that the moment of all the forces in the first force system about a point should be the same as the moment of all the forces in the second force system about the same point. That point I am choosing as O. Okay. What is the let's first write the right hand side. The right hand side is simpler to express. After all, there is only one such force acting, and that the moment due to that force would be RWO cross mg times E. Whereas the moment due to all forces from the first system will be RPO cross dF times E. dF is just a scalar here, and I need to integrate it over the whole body. That would be the moment of all the forces about point O, right? We equate the two. Also I replace dF by rho g times dV, and on the right hand side I have RWO cross E times g. I can express the left hand side as RPO rho g dB crossed with E. Crossed with E. After all, E is a constant as far as this integration over the body is concerned. Okay. Also, since G is a constant, I'm going to pull that out, or we can just simply cancel G in this way and then replace rho dV by dm, which is the mass of this small piece of the RB material, and thus we get right. Now recall that RPO integral divided by m is actually the position of the center of mass, Cm of Rb. So I have RCO cross E equals RWO cross E. Based on this equation, I conclude that the position W is nothing but same as the center of mass of Rb. And thus, it is logical that if we have to draw the free body diagram of an RB in the presence of gravitational force, constant gravitational force, instead of drawing this multiple arrows, I can draw the free body diagram in this way, where I put one single force, which is total mass of the RB multiplied by G, at its center of mass. That is what we usually do. What I have shown on the screen is the proof why it is the right thing to do, to put the total mass concentrated at the center of mass of the RB. So this is again an example of a situation in which the result equivalent force system is comprised of one single force acting at a special point. Alright. Note that in this case, the force system, the original force system, is not necessarily coplanar. All forces are not lying in the same plane, but it is a parallel force system. Further, it is a parallel force system and a distributed, volume distributed force system, and we got this conclusion.